Okay, let's get started. So, a couple of announcements before we get started. So, as I already mentioned, we have an exam this Friday. Okay, so it's going to be an evening exam. The exam is in ILC 140, S140. Don't come here. Okay, and at the last minute, make sure you go to the right room. I did put out a sample exam. It's actually a real exam from last year. You can use that as a basis to figure out what kinds of questions to expect on the test. Okay. The first 13 lectures and the guest lecture are covered. So, basically you should assume that whatever we do today is also going to be covered in some sense. So, that's something you want to keep in mind. Let's see. Oh, the second announcement is about the lab. As you will probably have seen, I put out lab 2. Okay. And you should take a look at it. I think we will have time after the exam, but don't wait until the last minute. One of the mistakes some people made is they got for lab 1 is they started too late and then they ran out of time. Okay. I don't think the lab is difficult, but it does take some time to do all the parts and all the bits and pieces that we have asked you to do. So, just start early and you should be fine. And of course, if you have questions, you should post them on Piazza, but first focus on the midterm exam. Okay. The other thing I do want to mention is if you are studying for the exam, you should first start with the slides and the notes. Okay. Don't start with the book and read the first n chapters of it. That would not be the right strategy, because whatever you are asked is what I have covered in class. If there is material in the book that I have not covered, you are really not expected to know that for the test. So, as a study strategy, just make sure you understand all the material that is on the slides. That would be the best way to study for the test. Any questions before we start? Yes, please. Oh, solutions to the practice exam. I look for them. I will. If I find them, I will do so. I think they should be there. Okay. Anything else? Yes. The guest lecture, yes, is all. Yeah, I did mention that on Piazza as well. Everything, including the guest lecture. Okay. You had a question? No. Okay. So, let's get started. So, just a brief recap from last time. We have last time covered the material on clock synchronization. I talked about synchronization algorithms, Christian's algorithm, Berkeley algorithm. We talked about how these form the basis for NTP, network time protocol. Okay, and then the last part of the class, I was talking about logical clocks or Lamport's clocks. And basically, the problem we were trying to address there was one where you want to reason about ordering of events. There are two events in a distributed system. You want to figure out which event happened before which other event. If that's the problem you are trying to solve, but you don't really care about the specific times at which those events occur, then you don't need real clocks or physical clocks. You can actually use the concept of a logical clock. And the notion of logical clock basically depends on message exchange, as we talked about last time. There's a picture here. So, essentially a set of processes that are exchanging messages, and by process of exchanging messages, they can impose an ordering of events across processes. And the very simple thing we said that allows us to do this is the message involves two events, the sending of a message on the first process and the receipt of the message, the second process. And since the message has to be sent before it's received, those two events are always ordered. And that allows us to order two events across machines. And then we said the property is transitive. Local events within a process are ordered based on execution order. And then if you send a message, the send happened before the receipt of the message on some other process, and all the events that are executed after a receipt are also ordered in the execution order. So, you can use transitive property to order events across processes. Okay. So, that was the high level gist. I showed you a very simple algorithm that uses integers to represent logical clocks and assign timestamps to events. This is a picture from the book that actually shows you a specific case with 3 processes where those timestamps are used. And this is just what happens without using Lamport's algorithm. And here we see that the Lamport's algorithm is used to adjust the timestamp whenever you receive a message by taking the max of the sender's clock, your local clock, logical clock, not physical clock, plus 1. Okay? And we will talk about that again in just a moment. The things to keep in mind is this is a partial ordering of events. It does not order all the events across processes. Specifically, events that occur after the send cannot be ordered with respect to another process unless there are more messages exchanged. Okay, events that are before the receipt of a message also cannot be ordered with respect to other processes unless there are other prior messages that have been received. So, you always get a partial order where you can take all the events on the sending process and events before the send, all the events on the receiving process and all the events after the receive, and those get ordered, but not other events. Okay. So, it is basically going to give us a partial order, and we will see how to fix that in two different ways today. Okay. The other thing I mentioned, which is a disadvantage of logical clocks or Lamport's clock, is it gives us the property which says if event A has occurred before event B, which is the property stated there. If A happened before B, then the timestamp or the clock value of A is less than the clock value of B. So, essentially, if you know that the event has one event has occurred before the other event, you use the algorithm, you will see that the clock values that get assigned have that property. Okay. But what this does not give us is, given two clock values, if you compare them and say that one is numerically less than the other, that allows us to say that A has happened before B. In other words, the implication does not go backwards, which is what we want if you want to compare timestamps and reason about order. It is only going in the forward direction, which says the events occurred in a certain order, the timestamp follow those orders. Okay, so, we want the implication to go both ways, and we will see how to address that today. Okay, but let me before that just say a few more words about how to convert a partial order into a total order. Okay, so, here is another picture, okay, which has three processes A, B, C. You will see that each has its Lamport's clock. What you have also done is you have appended the process ID to each of those clocks. So, you will see that this is process 1. So, this is this is clock value 1, 2, 3. You have appended dot 1 to it. Okay, and then this has you have dot 2 and dot 3. So, what this says is, now if you have partial order, you use essentially process ID to break ties. Okay, if you have two processes with event logical clock value 4. Okay. So, if you compare them, you do not actually get an order, but you are going to say it is 4.1 and 4.2. If these are process 1 and 2, that gives us an order. It is a tie breaking rule essentially. It does not actually tell us that is the order in which something has happened, but because these are partial order, for unordered events, we just use some tie breaking rule to get this partial order. Okay. So, that is an approach that many systems designer use to take Lamport's clock, which gives us a partial order, and convert it into a set of events that gives us a total order. Essentially, you are using the process ID to break any ties. That is the basic idea. Okay. Now, I am going to use this idea to show an example, and then we can look at how to do this using Lamport's clock. So, the example is a banking database. Okay. Specifically, it is a replicated database. So, this is a bank that essentially maintains its account in a database, okay, and that database is replicated on two sites. Okay, maybe there is a East Coast site and a West Coast site. Okay, now, every transaction that goes to this database and modifies it, okay, has to be performed at both of those replicas for consistency reasons. Okay, so, if you say add 10 or withdraw $10 from this account, because you go to an ATM and withdraw some money, you have to update the account balance so that that withdrawal is reflected on both the replicas. Okay. So, what that means is all transactions that are actually coming into the database have to be sent to all replicas, in this case both the replicas. Okay. But because there are many transactions being performed by many users, okay, that are being sent to the database, you want to ensure that there is also consistency across transactions. Okay. That also means that not only has every transaction to be performed at all replicas, the order in which you perform the transaction has to be the same on both replicas. Okay. If you have two transactions, okay, A and B, okay, you do not want to do transaction A before B on the first replica and B before A on the second replica, because that might lead to some errors sometimes. Okay. So, for example, let us say you only have $30 in your account. You withdraw 20, that is your first transaction, and then maybe there is a check you have written for another 20, and the second transaction will actually fail because you do not have enough money. if you perform them in that order. But if you perform them in the other order on the second replica, you will essentially get the first, the check will process, but your withdrawal will fail. So you will now have inconsistencies. So you don't want that to happen. You want the ordering also to be the same. Okay. Now, how will you ensure that the ordering is same? So one is you are going to use physical clock and timestamp every transaction. Look at the timestamp and just perform them in timestamp order. Okay. This requires physical clock and it requires synchronized clock across machines. Okay. And we said that that is always going to be a problem because synchronization is never perfect. Okay. The other thing you could do is use Lamport's clock to order all the transactions. So essentially a set of transactions coming in to any replica, you are going to use logical clock value to number them, and then you want to ensure that they are essentially executed in the same order, and we are going to use Lamport's clock to do this. Okay. And this is going to give us a new technique called totally ordered multicast. It uses Lamport's clock to get us a totally ordered multicast, a total order on the queries. Okay. This is the algorithm. I won't go into too much detail here because it is essentially using the total ordering example I just showed you, where every transaction is going to get a logical clock value, that's an event. Okay. Whenever you send a message to one database, you also send it to the other database. All queries or all transactions are replicated, which means they are going to be multicast to all the bank databases, bank database replicas in this case. Okay. So the way it's going to work is every update is timestamped with the sender's logical time, and then every message, which is in this case a transaction, is multicast to all machines. Okay. That is what is shown in the picture here. You will see there are two users that are making two different updates, and you will see that both updates are being sent to both replicas. The question is, how do you order them? Okay. So now what you are going to get is you are essentially going to get queries that are timestamped with the logical clock value. Okay. And now when you receive them, you got to order them somehow. Okay. You are going to use the totally ordered the total ordering example I showed you, where you are going to use the process ID to break the tie. So you will get essentially an order. Okay. Because if you receive a transaction with logical clock 2 from machine 1 and another one with logical clock 2 from machine 2, you are going to use the machine ID to break the tie. So one will have 2.1, the other will have 2.2. So you will use that to order it. Okay. It's an arbitrary way, but you found an order. Okay. And both machines are going to respect that order. Okay. But in addition, you want to ensure consistency. So you will, as soon as you get a message, you put it in the queue, you order it based on the timestamp, you send an acknowledgement, and then you process it only when all replicas have actually received your acknowledgement. Okay. So you essentially acknowledge that every machine has received the transaction, and then if you ordered it and you're at head of the queue, you are going to essentially take the transaction and process it. Okay. So this says that you not only ordered the transaction, but every replica has actually received your transaction and acknowledged it, which means that they all have the same order. Every transaction has been received successfully. Okay. Yes, question.
Is it possible that there are too many transactions, so the logical clock overflows?
Okay, that's a good question. Question is it possible that there are too many transactions and a logical clock overflows? Okay. And I did say that a logical clock is an integer. Okay. Now a conceptual integer never overflows. Okay. It can grow to infinity. Okay. So the concept of a logical clock does not depend on an integer with a finite number of bits. Okay. Because it's just an integer. It's like math, right? I mean, you don't have overflows when you're doing math problems. Right. Now, having said that, when you implement this system, you are going to use a variable that's an integer. It would be 32-bit or 64-bit or whatever the size is. Right. Now, that integer can actually overflow if you have lots and lots of events. Okay, if you have 64-bit integer, if your number of events is greater than 2 to the power 64, it will overflow eventually. So you want to make sure that whatever you use to represent your logical clock has sufficient bits that exceeds the lifetime of your application. Otherwise, you will eventually have an overflow. Okay. That's an implementation detail. It's nothing to do with the concept of a logical clock, because integers are integers. Okay. But when you write them in a program, they are actually integers with finite number of bits. Yes, question.
Couldn't you also run into an issue network communication such that your local queue keeps growing because you've got inconsistent clients sending updates up so that you can't get the multicast with all the replicas that you want? So you've got
Okay.
I get stuck. What about if I get stuck? Can't communicate with
Right.
the other
So you are asking about what would happen if there are network problem. Okay, if you are malicious clients doing bizarre stuff, this technique will not work. Okay, because you're assuming that you are well-behaved clients. Okay, assuming a well-behaved clients, you are asking a question, or if I understand your question right, you are asking what would happen if the network does not deliver some messages, right?
one client, like
Yes.
update one goes to
Yes.
one.
So you are simply asking what happens if update 1 goes to replica 1 update, but it doesn't go to replica 2, right? So that's essentially what you are going to say. So first of all, you have to, if you look at the algorithm, that can certainly happen. Okay, you will see that you are going to actually process a transaction only when it has been acknowledged by every process. That's a safety rule. It is put in place precisely for that reason, saying if the network loses your packet and your message or transaction never gets to the other replica, you don't want to actually perform that transaction. Okay? Because if you perform it, there's no going back. You can't undo a transaction that has been committed. So but if the message never even reached that client, it's not going to acknowledge that message. So that message is just going to sit in the queue forever, never get processed. Okay? So safety property is actually going to be preserved. Safety means nothing bad happens.
But the timestamp order, like if you have to wait
Yes.
for timestamp order.
Right. So you're right. So you are asking what happens in timestamp order. So thing that is going to happen is, first of all, you are not going to do anything bad that will cause problems. Okay? But that you will also not do anything good, because you are going to be blocked. You may be at the head of the queue waiting for an acknowledgement because you are the least numbered message. Okay? That acknowledgement never comes, so everything is blocked. Okay? So if you actually lose network messages, your liveness is not guaranteed. Liveness essentially is a property that says something good should happen, which means the transaction better commit eventually. Right? So you won't do anything bad, but you won't do anything good either. So of course that doesn't mean you will do anything at all, or means that you will not do anything at all. So you do want a reliable network to guarantee all of this, which means you want to use something like TCP, which is going to retransmit and eventually get your message there. Or your multicast better be reliable multicast, which means it will do retransmits or something to get your message there. But even if it is going to be unreliable, you won't do anything bad, but of course you will not make progress. So that's the downside. Yes, question.
Does this guarantee the real world ordering, or does it just guarantee
Right.
consistency?
Okay, the question is, does it guarantee real world ordering or does it guarantee consistency? So in this case, because you are using logical clocks and the actual clocks on those machines are not synchronized, that's our assumption, we are not actually guaranteeing the real world ordering. We just find an ordering that everybody agrees to. Okay? If you want to guarantee real world ordering, that's a bigger problem, and we'll look at that when we talk about consistency in a few lectures. Is that clear? Why? Because if you want to guarantee real world ordering, you have to timestamp those messages. The clocks have to be synchronized. Okay, and then you have to make sure that you respect those timestamps, and clocks are never perfectly synchronized. So there are all sorts of issues you have to deal with. Okay, there is no perfect clock. Is this clear so far? Okay. So now with that background, we are going to look at a generalization of logical clocks, which basically takes that logical clock algorithm and adds a new dimension to it. So we are going to repeat what we said last time, and then we are going to see how to make it better. Okay? And the property we want is twofold. If event A has happened before event B, you want the timestamp of A to be less than timestamp of B. Okay? Also, if you are given two timestamps of two arbitrary events in the system, and you compare those timestamps and say this timestamp is less than this other timestamp, you should be able to say that this event has actually happened before that other event. Okay? In other words, you want the implication to go both ways. Okay? Because Lamport's clock has the first property, if A happened before B, C of A is less than C of B, but it doesn't actually guarantee the opposite. And now we'll see how to get that property as well. Okay? To do this, we actually have, and that property, by the way, in distributed system is called causality. Okay? If A happens before B, then A is also causally related to B. There are other things you can do with causality, which we'll come back to, which says causal delivery. You could have a network property that says if send of M has happened before send of N, which are two messages, and you can order their sends, then the delivery also happens in that order. Okay, so you can ensure that you can order messages based on the sending, which one has sending events. Okay? But we won't talk about how to do that. What we'll first talk about is how to ensure that the property goes both way. Okay? In other words, now we need a timestamping mechanism that says the timestamp of A is less than timestamp of B, then A should have preceded B, causally preceded B. Okay, so how are we going to do this? So I'm going to use pictures to show this. I think there may be a. Okay, so there's an algorithm here, but I'll just explain that using pictures. Okay. So now we are going to essentially assume the same setup as last time. Okay. Some number of processes. Okay, we are essentially, let's start with maybe 3. Okay. There's process A, B, and C. Okay. Each process is going to keep a logical clock that's an integer. Okay. You are going to tick that logical clock whenever a local event occurs, okay, like before. Okay. However, what we are also going to do is rather than keeping a single clock value, each process is going to maintain a vector of clock values. Okay. So, one for each process in the system. Okay. So, essentially all clocks get initialized to 0, 0, 0. Okay. For process A, the first element is its logical clock. The other two elements is what it knows about the other two processes, their logical clocks. Initially you know nothing, so you just initialize to 0. For process B, the second element of the vector is its logical clock. The first element is what it knows about A, and what it knows, third one is what it knows about C, and so on. Okay. Every time an event occurs, so if you are process I, you are going to increment the ith element of that vector. Okay. That's like logical clock. So this one, when the first event occurs, becomes 1, 0, 0. This one, when the first event occurs, is going to become 0, 1, 0. And this one is going to be 0, 0, 1. Okay. So if you are a local event, the ith element of that vector for process I gets incremented, which is like logical clock. You're just ticking the clock. Okay. Now, when you send a message, like before, you have to piggyback the vector clock onto that message. Okay. So let's say there is a send of a message here. Okay. So this is now 2, 0, 0. You send a message. Okay. So that message, in addition to the actual message itself, is going to take the vector clock with it. Okay. Now, when you receive the message, you are going to take the vector clock that arrived on the message. You are going to take your local vector clock, okay, do a max of the two vectors, which means you take each element and do max of each of those element, and then you take your ith element also. Okay. So essentially this will give us 2, 2, 0. Okay. Basically you take max of 2 and 0, that gives you the first element 2. You say 0, 1 is 1, but then you tick that element because you are the second process, and the third one is still 0. Yes. Okay. So essentially you are going to do max of the two vectors. Okay. You are going to do max of this vector, your vector, plus 1 for the ith element. Okay. So you take, and how do you do a max of two vectors? You take each element of the vector, take the max of those values. Okay. So if you take the max of this, you should get 2, 1, 0. Okay, because that's 2 is the first element, 1 is the second, and 0. And then you increment the ith element, which is the second one here. So that becomes 2, 2, 0. Is this clear? Okay. And then so on. So now if there are further events here, that becomes 2, 3, 0, and so on. Okay. So let's do one more send and see what happens. Okay. So let us assume that this process is going to send a message here. Okay. So essentially the vector that goes is 0, 0, 1. Okay. So what do you think will be the vector here for the receive? Okay. So it should be 3, 0, 1. Okay. Okay. So that's your vector clock algorithm. Okay. And now we are going to claim that this algorithm actually gives us the property we want. Okay. First thing is, let's see if two events precede one another, that the vector clocks are ordered. Okay. Locally, this event has preceded that event. This clock is less than that clock. That event has preceded that event. You get that property. Okay. Send and receive are ordered because the receive is always max of the two vector clocks. Okay. So by definition, the receive will have a greater vector clock value than the send. because you are doing max and then you take one, you increment one of the elements. So, that is going to give us that property and so on. Okay. So, if A has happened before B, it should be possible to convince yourself that the vector clock of A should be less than vector clock of B. Okay. You have a question? Yes.
If A sends some message to B, let's say 200,
Yes.
and that message is not transferred in the first place. Let's say you're using a TCP and the message is not transferred. Now some event occurred at A and now A's logical clock is at 300, and now A is trying to send the same message again to B. So what will be sent, 200 or 300?
Okay. So, question is, I'll repeat the question. The question is, let's say you sent a message, but it has not been received. Let's say the packet got lost. Okay. And then another event occurred on that process, sending process, its clock has got incremented. You might time out and resend the message. You should it get the new clock value or the old clock value? That's your question. So, the simple answer is it should just get the old clock value, because it is just trying to send the same message. It's not a new message. If it was a new message, you would say, use a new clock value. If you are just still trying to resend an old message that needs to be retransmitted, you use the clock value of the original message. Okay. Okay. So, now let us ask the question, if I give you two clock values, okay, two arbitrary clock values in the system, can you reason about the ordering of event and say something? Can it actually guarantee us the property we want, which is that essentially vector clock of A is less than vector clock of B, A has happened before B. Okay, so, let us take two arbitrary clock values, right. So, let us take this event and this event. Okay. I am going to use okay. If I look at this, what does it tell us? Which vector is greater? Okay, second vector is bigger. Okay. Does this also, now if you look at these two events, can you say something about the ordering of events? Okay, so, you should be able to convince yourself that the event labeled 100 has happened before the event labeled 230, and this comes from the transitive property again. The send has happened before the receive. You cannot send a message before it is received. Okay. That is clear. Okay. So, this send and this receive are ordered. Okay. This event has executed before that event on that process. So, within that process, this event has happened before this event. Okay. This event labeled 230 has executed after the receipt event, and hence those two events are ordered. Okay. So, you just use the transitive property. If this has happened before that, that event has happened before this, and then that one you will get that 100 has happened before 230. Does that make sense? That is not a proof. Okay. Do not ever think that what I did is as an example. But yes.
If we take the other example of 0, 0, 1 and 2, 0, 0.
Yes, we are going to take more examples. Just give me a second. Okay, so you can take any two events that you can see from this timing diagram has the happened before relationship between them, and you can look at their vector clock value and you will see that they are even, and that should be clear because here you are incrementing the local value, and once you send that vector clock here, this has the max of the two. Okay, if this is greater than this and this is greater than this has to be greater than that. Right, because based on the max property. So, you can convince yourself that that property is true. Okay. Now, let us take some other events. Okay. In particular, I am going to take this event and this one. Okay, so, I am going to write them here. And okay, what is the relationship between these two vectors? Yes? You can't say, but first you should say what do you mean by greater than. I never defined what vector, what it means to say one vector is bigger than another, greater than another vector. Okay. So, first we got to define what, I mean, you know, when you compare two integers, when one integer is greater than the other, but you never said what that relationship meant for a vector. Okay. And it is the same thing. Okay, we will say that vector A is greater than vector B, okay, if every element of A is greater than or equal to every element of B, and there is at least one element in A which is strictly greater than B. Okay, that is what we mean by greater than. Okay. So, if you look at all the entries, they have to be at least equal and there has to be at least one that is greater. That is what we will define to be a greater relationship for two vectors. Okay. Now, what does that mean for these two vectors? Here the first element is greater than the second one is less than the first, first has the second element here is less than this one, and the third one is greater. So, in this case you cannot define them because some elements are greater and some elements are less than. Okay, so, in this case what we say is the greater than relationship is undefined for this vector. Does not mean that every two vectors have to have a greater than relationship, it could be undefined. Okay. And that is absolutely the right thing, because if you look at these two events and I asked you which one happened before the other one, what would you say? Okay. They are concurrent event because there is no message exchange between B and A yet. Right. Message events only get ordered if there is a message exchange. There is no message exchange for certain events, those events cannot be ordered, they are concurrent events. Okay. And you will see that those two processes haven't even exchanged them. There is no message that has gone from B to A yet. Okay. So, you cannot actually look at this figure and say that there is any relationship between the two events. Okay. Hence, the relationship is undefined, and as a result the vector is also not, if you look at their vector values, they are also not telling you which one is greater than the other. Okay. So, this is precisely, this was not the case when you had logical clocks. If I go back to the picture I put up last time, since logical clocks are single integers, you can always compare them even if the events are concurrent. Okay. And so that gives us, that does not give us the reverse property, because you can order any two integers even if they are not concurrent event, and hence you can't just look at the values and reason about events. Okay. In this case vectors get ordered only when there is an actual happened before relationship between, otherwise they will not get ordered, they will remain concurrent. Okay. The vector values will be such that some elements are greater and some elements are less, and hence the relationship remains undefined. Okay. And because these are again not, is not a formal proof, but this should convince you that now the relationship goes both ways. If you actually get any two vector values and you can order them, you can say that event has happened before the other event. If you cannot compare the two vectors, you can say those are independent or concurrent events, we cannot order them. Okay. Still partial order, but the relationship now, the implication goes both ways. Okay, so, this is called vector clocks, it is a generalization of Lamport's clocks. Any questions here? Should we do any more examples? Yes. Is there any way to do total ordering? So, total ordering is arbitrary, because if you take any two events, you can always use a tie breaking rule to do total ordering. But I mean, if you really want total ordering, you should just do Lamport's clock, because it still gives you partial order, and then you add a tie breaking rule, right? Because concurrent events technically cannot be ordered. So, you can just make an arbitrary order out of them based on a rule, but that does not mean that was the order in which they actually occurred. Okay, so, it still technically only gives partial order. Any other questions here? Yes, please. What is the overhead of vector clocks? So, first of all, if there are n processes in the system that are exchanging messages, your clock has to have n integers in it. Okay. Clock value is a vector, and as the number of processes grow, that vector is going to grow. Okay. Furthermore, every time there is a message exchange, you have to piggyback the clock value with the message. Okay. That is a small overhead, because there is still a few integers, hopefully few integers. The thousands of processes, it will be a large integer, but still there is still an overhead of message exchange. So, beyond that, between Lamport's clock and vector clock, there is not a whole lot of difference. You just have to keep bigger vectors and send them whenever you transmit messages. Yes, you had a question.
So, would that be an advantage? So, for example, when A sends a message at 200 to B, if you increment B's logical clock at the time of sending, couldn't you get So instead of 200, you make it 210 when you send a message to B. So if you do that, then when you compare the vectors, won't you be able to get a strictly greater than or not greater than relationship between them?
So you are asking what if we actually incremented the receiver's clock, which anyway the receiver is doing here, by the way,
Yes,
but you are just doing it at the send, right?
You don't have feedback for that at A. So if you do it at the time of sending, then couldn't you compare those two clocks?
Okay. The question is, if you actually incremented the receiver's clock at the sender and sent it, could you not compare them? Okay. There are many ways events could be unordered. Okay. Could you then take A and C that have never exchanged any messages? Okay. So if there are two processes that are never exchanged messages, this will not work. It will still remain concurrent. Okay. Our goal is not to impose a total ordering. You only derive an ordering when there is a message exchange that allows us to see that ordering. Okay. So that's the point. In your simple example, when there's a message exchange, you may be able to do something more between those two pairs of processes, but it doesn't still address that process and some other arbitrary process which hasn't had any message exchange. Okay. So those clocks will not be comparable. Any other questions? Okay. So we will continue from, we'll move on from vector clocks and look at some other things you can actually do with vector clock. So this is just another example from the book. This essentially does what is called causal delivery of messages. So essentially what it says is, if you are sending messages and you want to have causal delivery, which is send of A has preceded the send of B. Okay, if you know that, then the receipt of A has to precede the receipt of B. You can't reverse the delivery of those messages. Okay. If you have only two processes, that is just saying in order delivery. You send two packets to a process, you have to receive those packets in the same order. Okay, if you are just two processes in the system. But you have multiple processes that are exchanging messages. If send of A has preceded send of B, then the receipt of A has to precede receipt of B. So what this essentially says is, if every send, as in this case we are ticking a clock only when there is a send and then piggybacking that message. So what happens is, here process 0 has sent two messages, multicast a message, no, hasn't sent two messages. That message has been received at P1. Okay. And then P1 sends a message after it has received the first message from P0. So that's this message M star. Okay. And that message actually reaches P2, and maybe it reaches P0 and it reaches P2 first. But because that has a vector clock of 110, it will not be delivered, because P2 in this case can infer from this vector clock that there is actually a message that P0 sent that hasn't yet arrived here. Okay. Because you are multicasting every message and ticking the clock on every send. Okay. If you receive messages out of order, you can just look at the clock values and say, this is the first message from 2 that has just come, but there seems to be 2 seems to have received a message from 1 already, which is why its clock got incremented. I have still yet to receive that message, so I'll hold off on delivering this message, wait for that message which may have taken a longer time to arrive here to arrive first, then take delivery of the message. So just by looking at clock values, okay, you can also reason about what other processes have done in the system. Even though that message came from P1, you can actually see that there is some message that P0 has sent, which P1 has already received, but you have not received. Okay. So in other words, this simple example tells us that vector clocks, okay, by keeping track of clocks of other processes, you can figure out what events you and other processes that are communicating with you have seen from that process. Okay. So that's essentially the essence of a vector clock. It is telling you what is happening at different processes with respect to clock values and what have you seen. Okay. If you have never seen anything from a process, that element of that vector clock will remain at 0, because there is nothing you will actually see that causes you to increment that value. Okay. So you can reason about other interesting things. This is just an example to show you that there is some interesting aspects to vector clocks beyond just the vector clock algorithm. Okay. So with that, I'm going to actually go and talk about a different problem, which is global state and distributed snapshots. Okay. So we are switching gears. We are kind of done with the topic of synchronization. Okay. We did physical clock synchronization, algorithms, Christian's algorithm, Berkeley algorithm, NTP, and then we looked at 2 logical clock algorithms, Lamport's clocks and vector clocks. Okay, so we have done 5 techniques already. Okay. So that's all we will have to say about synchronization. We'll move on to the next topic, which is going to be global state of a distributed system. Okay. So let me explain what this even means. Okay, what we mean by global state, why should we care about it. Okay, so let's take an abstract example of a distributed application. Okay. Assume that there are application that runs on n machines. Okay, let's say it's a simulation that you run. Okay. You started a simulation is running on n machines. Okay. Let's say at some point in time, some process on machine I crashes. Okay, it just essentially there's a software bug or maybe there's a hardware issue, the process just crashes. Okay. Your n-1 processes are still computing, but because one process has crashed, you are not going to get your end result. Okay. So the typical thing you would do in this case, what would you do? Actually, let me ask you. Okay, you can terminate all processes and restart from the beginning. That's the simplest thing you will do, and restart the computation. Okay. But you can see that this is going to waste CPU cycles, because if your processes had computed for maybe several hours, you lost several hours of computation time, you are going to redo everything from beginning. Okay. So other thing you could do is periodically save your state. Okay, you can essentially periodically checkpoint or save the intermediate results of your computation. Okay, saying until this point, this is what I have done so far. Okay. And now if you terminate the processes, you can start from the most recent saved state and then start from that point. It doesn't waste all the cycles that you have spent on that computation so far. Okay. Is that clear what I just said? Okay, so rather than starting from the beginning, if you periodically save your current state, okay, which is whatever you have done so far, intermediate results, you can load those results and restart. Okay. The question is, how do you do this in a consistent fashion? How do you do this so that you can actually load that state on all n processes and continue from that point? Okay. The problem is trivial if all clocks were synchronized. If you had a perfectly synchronized clock, you would say at the end of every hour, every process should freeze, suspend itself. Everyone should write their state to disk, and everyone should continue. Okay, so everyone is checking their checkpoint at exactly the same time. So it should be all consistent. Okay. But as you know, there is no such thing as a perfect clock. You can't have perfect clock synchronization. There's always going to be some error. Okay. So even if you said everyone should freeze at the end of the hour and checkpoint, okay, the clocks are slightly off from real time. So some clocks may be a few microseconds past the hour, some maybe a few microseconds before. So you are not actually taking a snapshot at exactly the same time anymore. This is going to give you inconsistencies, because if you take snapshot at arbitrary time and load that snapshot, is not going to give you consistent results. Is that clear what I said? Okay. So this problem of saving state of a computation in order to start it from a consistent state is not a trivial one. Okay. And global state essentially says that this is the memory state of every process, and you will see that it also says it also has all the processes messages that are in transit. Okay. And you have to somehow capture this in a consistent fashion, even in the absence of clock synchronization. Okay. That's the problem we want to solve. The reason we want to solve this is because you have lots of computations that are long running. If there are some processes fail, you don't want to restart everything from beginning. You still want a way by which you can keep saving your state and start from wherever you left. The question is, how do we do it? We'll get to that in just a moment. But to understand that, we'll now introduce this notion of a global state. That's essentially the state of all the processes, so that you can save that in a consistent fashion. Right? We're going to say that's the local state of each process, and messages that are in transit. They have been sent but not received. They're somewhere in the network. You want to save all the memory state and messages in transit. Okay. So we will assume that there is no global clock or no synchronization, and yet we want to capture a consistent state. And I'll give you some examples of what it means to capture a consistent state versus not. Okay. So here are two timing diagrams. These are 3 processes P1, P2, P3 that are part of a distributed computation. Okay. If you had a perfectly synchronized clock, you would essentially freeze them all at the same time. So, you would essentially say this is the time that everyone should freeze, write out your state, continue. Okay. But clocks are not synchronized. So, even if you say everyone should take snapshot at noon, okay, because noon is slightly different on each machine because they are not perfectly synchronized. This machine sees this time to be noon, that machine sees that time to be noon, and that machine sees that time to be slightly off from one another. Okay. So, they all still stop at noon, but they are not actually stopping at noon. That is what when their clock says it is noon. Okay. So, now you are taking snapshots actually at different points in time. As you will see, the dotted line essentially says when you are trying to save your state. Okay. And the question is, if you did this, will you get consistent results? If you freeze exactly at the same time, you should get consistent result. Now, you are trying to do the same thing, but with clocks that are slightly off, because clock synchronization is not perfect. And then are you still going to get consistent results or not? Okay. So, then we should ask, what does it mean to get consistent result? What does it mean? Okay, what it means is if you actually restart the computation from wherever you took that checkpoint, you should essentially get the same end result as if there was no crash at all. You just started from the beginning and ended. Okay. So, in this case, the simple thing that is actually going to change the results of the computation is if some messages either get lost or some messages get duplicated, okay, as we will see in just a moment. Okay. So, we will claim that even though this snapshot is not being taken at exactly the same point in time, this is what we will call a consistent cut or a consistent snapshot, but this same example here where the clocks are off in a different way ends up being inconsistent, and I will say why that is inconsistent. Okay. So, if you actually do this, what is shown in the second scenario, same processes, but you end up taking snapshot at slightly different times, you will see that if you restart the computation from wherever the dotted line hits each of these processes, you are not going to get a consistent result. Specifically, what is going to happen is in this process P3, message M2 has already been received and processed, okay, because you took the snapshot here. Okay, you already saw that message and you are taking a snapshot after that. Okay. Process P2 has taken a snapshot here. Okay. If you restart process P2 at this point and it continues execution after a crash, say, then it is going to resend message M2 because that is what happens in its execution. Okay. So, now you will see that process P3 has already processed M2 and it has saved its state and you restarted it. Now, M2 is actually resent to you because P2 has actually started from this point on and sent M2. Okay. This is only because you are taking snapshot at different points in time. If you had taken a snapshot exactly at one point in time, this would not have happened. Okay. So, M2 has been received twice. Okay. If process M2 said add $100 to this person's bank account, you would process it twice and get an inconsistent result. Okay. You may be happy, but the bank won't be happy. Right. So, you don't want this kind of problems to occur. Okay. So, now put another way, what has actually happened is a message has been received in the cut that has actually not been sent as far as this point in time is concerned. So, you are resending that. Okay. So, you never want to take a snapshot where the receipt of the message is on the left of that snapshot and the send is on the right, which is what has happened here. It is okay for messages to cross, okay. But if they cross that dotted line, the send better be on the left. It should be in the before part and the receipt better be in the after part. If you have the opposite where the receipt is before and the send is after, that message is going to get duplicated if you restart that computation from that point on, and that is going to give you a wrong result. Okay. So, even though you may not have synchronized clock, you still want to avoid the second case. It is perfectly fine to have the first case, okay, except that you want to ensure that all messages that are in transit that actually cross that dotted line should also be saved as part of that snapshot. Okay. This is why we said that the global state of a computation is the local state, which is the memory state of each process, and all the messages that are in transit. Okay. Because if a message is in transit, if you restart it, it's not going to get resent. You have to save that somewhere and say this message was in transit and redeliver that to that process, or not redeliver, deliver that to that process. Okay. So, you want to ensure both of those properties. And this is precisely to ensure that messages which cross this dotted line are the ones in transit. If a message is completely on the left, it has been sent and received, it's done with. The message is completely on the right side of the cut, it means that it has not even been sent and will be sent later time and received at a later. The ones that cross, you got to deal with. So you essentially want to save the TCP buffers and the memory state. That will do it. The TCP buffer will have all the messages in transit, and the memory state will have all the memory state of the computation. Okay. We still haven't said how to do it, okay, because clocks are not synchronized, but you need to know what has to be done. Okay, now we'll see how to do it. Any questions on this? Yes.
On restart, are you saying that all the processes go back to a previous state?
Yes. So if you say that, let's say process P2 crashed. Okay. If we had not taken any checkpoint, we would start all process. We'll terminate every other process because P2 has crashed, and we start everything from the beginning, and they'll just start the computation all over again. That's fine. Okay, but you wasted some time. In this case, okay, if you restart, what you're going to do is you will essentially load that state for P3 and start that process from there. You will essentially restart P2 from this point, and you're going to restart P3 from that point. Okay? And you want to ensure that because they are not starting from exactly the same time, you're still going to get the same end result for that computation. You're not going to get some different answer to whatever you're doing. Okay? So that's what we mean. Yes.
Clarify again why in part B, sender of input cannot be identified with this.
Okay, well, forget the label, what it says. Okay, first we'll ask why this is the wrong thing to do. Okay, so the question is, why is this inconsistent? Okay, where does the inconsistency come from? So now we'll see again the same example. P2 has crashed. Okay, we are going to now terminate all processes and restart them from the most recent saved state. For P3 is going to start from this point. P2 is going to start from here. P1 is going to start from there. Okay? So they basically now restart computation from that point and they continue. Okay? What is going to happen next is P2 will continue execution, and at this point is going to send M2, because that's what it does during its execution. Okay? P3 has already started from a point where it has seen M2 and processed it. Okay? If P2 resends that message, there are two messages sent. Okay, and that is going to result in an inconsistent end result, because M2 will be processed twice. And if it is going to change the state, like increment this variable, that variable gets incremented twice. It could be an RPC. Same RPC got processed twice. So you don't want that to happen, because in the original computation, there's only one message. Okay? So the reason this happens is the receipt of the message is before the cut, and the send of the message is after. Okay, so essentially, it's a case where the message has been received in the snapshot, but it hasn't even been sent. So you don't want that. Okay, that's the inconsistency. Yes. Go ahead.
Like you are starting the process after the dotted line, right after the dotted line. So where is the state exactly saved for that? You're saving some state, right?
Yes. The question is, when you restart the process, where is the state saved? That's your question. Right. Right. So what this simply says is the following. Let me explain what we mean by saving state. So remember when I said you had perfect clocks, I said at noon or at the hour, every process should freeze. Okay? Take all its memory contents, write it out to disk. Okay? If you had perfect clocks, every process would stop exactly at the same time. It would take its memory state and it would write it out to disk. And our assumption is, if you take that memory state that was in disk and bring it back to memory, you are exactly where you were and you can start from there. That's our assumption. Okay? Now in this case, because clocks are not synchronized, you still say every process should freeze at noon and write its state to disk. But noon is slightly different on these processes because their clocks are off. So this clock sees noon at this point in time. This is real time. Okay? But it thinks this is noon, this process thinks that is noon, and that process thinks that is noon. So they're still doing the same thing. At the end of the hour, they're pausing and writing their memory contents to disk. And the question we are asking is, if we take those saved contents, we reload them and restart the computation, what is going to happen? Because that means I restarted from wherever that dotted line is intersecting those processes. Okay, yes? Could you fix this with a vector clock? We will fix it in just a moment. We haven't seen how to do anything yet. We just said what is the problem. There are vector clocks to do this, but there are simpler algorithm. Okay. Yes. Okay, that's a good question. Okay, let me repeat the question. Question is, what happens to M3 if it just restarted the computation? Okay, because P1 is starting from a point after it has sent M1. Okay, it's just going to continue from that point on. It is not going to resend M1. Okay. P2 is going to start from this point on. Okay. It hasn't yet seen M3 because it had basically not seen it. Okay. So if you simply save the memory state of the processes and just start them from that point on, you are going to lose all messages that are in transit, that have been sent but not been received. They're somewhere in the network. Okay. This is why we said snapshot essentially means save the memory state, but also save all messages in transit, which means save the TCP buffers, which actually in the OS hold all the messages that are somewhere in progress. Okay. So what would happen in this case is M3 would either be in the TCP buffer of the sending process P1, or it would be in the TCP buffer of the receipt process, but not yet delivered to the application because it has not been seen. Okay. So if you save those buffers and reinstantiate those buffers, you will recreate the message. You don't have to send it at the application level. It's somewhere in the network. It will get sent. That's the point. Okay. So M3 will actually get delivered eventually because you are saving the memory state of the network as well in some sense. Anything else? Okay. So now with all this, let's ask the question, how are we going to do this? So the technique you are going to use to take a snapshot is called a distributed snapshot algorithm. It does not assume any clock at all, okay, because there is no synchronized clock. So why bother? Yet it will always give us a consistent cut, because it will give us whatever we wanted. Okay. And the picture that you want to keep in mind is the following. Okay. So this is basically an analogy, not how the technique works. Okay. So think of, let's say you want to take an actual snapshot, meaning you want to take a photograph. Okay. Let's say you are taking a photograph of the sky. Okay. Maybe there are birds flying in the sky, there may be clouds, or there's something in the sky. Okay. Now assume that your camera on your phone or whatever camera you're using does not have a field of view that's big enough to take that entire sky in one photograph. Okay. So you can't take the picture of the entire sky. So the way you are going to do this, you are going to take pictures of different parts of the sky, okay, and you are going to piece it together. Okay. And you want to take a picture, you want to take all of these photographs in a way that you consistently capture the state of the sky. Okay. What does that mean? Okay. Let's say, as I said, there are birds flying around. Okay. So every bird that was flying around better be in some picture somewhere. Okay. You don't want a bird to be in a picture when you took it here and then the bird flew here, you took a second picture and the bird appeared twice. Then you are miscounting the number of birds. That's like double counting messages. Birds are messages in this case. Neither do you want a case where you took a picture here, there's no bird, and then when you took the picture here, the bird flew off and went to the other part. Okay. Then you missed a bird. That's like you lost messages in the network. Okay. So you want to still take these pictures at different points in time, yet capture the state of the sky as it existed in some consistent fashion. You can't take the pictures all at once because we don't have synchronized clock. You're taking them at a slightly different time. But everything that's important, that's represented in the sky, is also captured in the picture. Nothing is lost, nothing is duplicated. Okay. You want to do exactly that here. Okay. Photographs are like snapshots you're taking of processes. Birds are messages that are going from one process to another. So we want to do the same thing here. Okay. So this is what we mean by, that's why it's called distributed snapshots. Yeah. So we'll use a very simple technique, okay, and then we'll see why it works in just a moment. Okay. So I'm going to actually use a picture again because that is harder to explain than just using pictures. Okay, so I'm going to take three processes, number them, P1, P2, P3. Okay. In this case, we'll assume that processes, there are n processes, and some subsets of them are communicating with one another. Okay, through, let's say in this case, we'll just assume that TCP channels. The TCP is a good way to communicate, so we'll assume if process P1 is communicating with P2, There is going to be a TCP channel which is a duplex channel. TCP is always duplex communication. You can send and receive on the TCP socket. Okay. And then we'll assume again, maybe in this case we'll just take a simple example where processes are actually communicating with all other processes in the system. Okay. So we'll assume that now we want to take a snapshot. Okay. There's no way to say let everyone should freeze exactly at noon and take a snapshot, because there's no synchronized clock. So we'll say any process can start the snapshot algorithm. So in this case, P1 says it's time to take a snapshot. So it's going to take its memory state and it is going to store it on disk. Okay, so it just saved its memory state to disk, and it's going to send a message to every other process saying please take a snapshot. Okay. This special message is going to be called a marker message. Okay, so it already has open socket connections to other processes. So you just send a marker message on your outgoing channels. Okay, marker message is simply an indication take time to take a snapshot. Okay. That message is going to go over the network and arrive, let's say it's going to arrive at P2. Okay. When P2 receives a marker message, it says it's time to take a snapshot. So it's going to say let's do take a snapshot, write its state to disk, and it's going to repeat on every outgoing socket. It's going to send a marker message saying please take a snapshot. Okay. So in this case, the two outgoing channels are a message going back to P1, and there's a socket connection to P3. So it's going to then send a marker message here, and then it's going to send a marker message down here. Okay. The one additional thing that a process is going to do is as soon as it receives a marker message which says time to take a snapshot, it also starts saving every incoming message in its TCP buffer to disk. So all incoming messages are also being logged at this point, in addition to storing its memory state. Okay. So in particular, when P1 took a snapshot, it not only saved its memory state, but all its incoming sockets is going to start saving these messages. So that's basically this one and this one, until you get a marker message back on those channels. Okay. So now this, so there's a marker message going from P2 here, there's a marker message going from P1 to P3. One of them is going to reach first. Okay, because your two marker messages in transit to P3. Let's say the one from P1 reaches here first. So it's going to say time to take a snapshot. It's going to write it save to disk, and then it's going to send a marker message out here. It's going to send marker message outgoing channels, and it's going to start recording. And as soon as the second marker message comes, if there are additional messages, they'll all get saved to disk. And when this marker message arrives, it will stop recording. Okay? Because the arrival of a marker message, the arrival of the first marker message says it's time to take a snapshot. Okay? And then you start recording on all other incoming sockets until a marker message actually arrives on those channels, and then you stop recording. That's a simple rule. First time you receive a marker message, save your memory contents. Start recording all incoming packets. Okay? And when you receive a marker message on all those other channels, stop recording. Okay, that's the algorithm. We'll see why it works and what it does. Is it clear what it is doing first? Then we'll see why does it get us a snapshot. You had a question? Yes.
Once the process has sent a marker, does it continue executing or does it wait for the other marker?
Okay. Question is, once the process has actually saved a marker, does it continue executing? Yes. As soon as you're done, you basically received a marker or you initiated the algorithm, you save your state, you send out marker messages, you just continue executing, but you still keep recording incoming messages. That's all you're doing. But you are executing, you're not frozen. Okay? So you can continue execution. Okay? So now you can ask the question, why does this actually give us what we want? Is it going to give us a consistent cut? Okay? And does it actually get us all the processes state and all the messages in transit? Okay? So the first thing is you have to realize that if you send a marker message on your outgoing channel, you are going to always receive a marker message on your incoming channel. Okay? Because that marker message will reach the other process, and then that other process has to send marker messages on its outgoing channel. So your outgoing channel is somebody else's incoming channels and vice versa. Okay, so if you send a message this way saying start, it will go here and then it will start the snapshot algorithm and send a message this way. So eventually you will get back a marker message on that same socket the other way that will tell you that it's time to stop recording messages that were coming in the other direction. Okay. So in other words, your algorithm will terminate eventually. It's not going to sit in an infinite loop forever. Okay. Because every socket connection can be viewed as a duplex connection. The moment a marker message goes out at the other process, okay, it will basically, you will get a marker message in the other direction. Okay. Second is you are also saying all the messages in transit, because those are precisely the messages that once you're taken a snapshot and you're told your other processes, they may have already sent you some messages that you are not saved, have not processed. Okay. And because you're now recording your incoming channels until a marker message comes back, you're also saying all the messages in transit. Okay. Those were messages like M1 in this case, okay, or not M1, sorry, M3 in this case. Okay, so you took a snapshot, you told the other process to start saying record messages, and these are the messages that you are going to save, and then if you restart the computation, you will reinstantiate them in your network buffers. Okay, so I'm going to show some pictures here. These are from the book. So here is the same example shown here. So you can see that there's an incoming socket, there are multiple outgoing messages. So the first time a marker message arrives, okay, what you do is you essentially take that state, memory state, and say to send marker messages on outgoing channels, and you start recording your incoming. So in this case, this incoming is that same channel. So you will start recording A, B, C, D, and then a marker message comes back, and you're done. Okay. So your state is essentially your memory state, and messages A, B, C, D that were in your socket buffers, those were the incoming messages. Okay, that's exactly what that technique is doing. Okay. So you don't need the snapshots to be taken in a way that requires synchronized clock. You can take them at different points in time, so long as you have saved the memory state and you have saved all the messages in transit, you will still get the same end result for your computation. Because if you restart from that point on, you will essentially take all the messages in transit and reinstantiate them, and you will essentially have a consistent cut. You will not lose any message, because you are saving messages. That should be clear. This is TCP, so we don't worry about network losing messages. It is a reliable channel. That's what TCP gives us. Okay. Neither are you going to have messages pop up twice. If you processed it, it's not going to be resent. You're only taking messages that are actually in progress and saving them. Okay. So that's the basic intuition behind this technique. Okay. So let me pause and ask questions. Ask for questions, not ask questions. I can ask questions as well. Yes.
So I mean, if one of the processes fails during this time, it just goes back to the previous.
Yes. So the question is, what happens if a process fails during a snapshot? Okay. If you have failures during a snapshot, that's a partial snapshot. It's not complete. So you got to go back to the previous completed snapshot and start from that point. Okay. So you can't take a partial snapshot and restart. Yes.
Is TCP buffer part of the local state?
Okay. Question is TCP buffer part of the local state? TCP buffer is not part of the memory state. Okay. So if you see the picture, which is drawn a little better than what I did there, this is process Q. Okay. That is the memory state, that gray box in there. Okay. These are all the messages that are essentially coming from the network. So you can think of these are all TCP buffer messages. Okay. So what you are going to do is you are going to save the memory state, and separately you are going to take all the messages that are arriving in your TCP buffer and saving them as well. Okay. So they will be eventually part of the state. As you see here, what you have saved is your memory state and all the messages. Okay. So by local state, I mean they are not part of the memory state. They are still part of the state that gets saved on your disk.
Wouldn't it be easier to just also save the state of the TCP buffer and just discard all messages that are on in the routers in between?
Okay, that's a good question.
I would just say I would use them anyway.
Okay, so this is a different suggestion. It says, why do this? Why not just save the memory state and whatever is in your memory buffer and discard all the messages that are in the routers? Okay. So if you do, you could modify the algorithm, but then you have to save not only the incoming buffer, but also the outgoing buffer, because any messages that are actually in the router somewhere are also saved on the send buffer of the sender, because they have not yet been acknowledged. This one is only saving the receive buffers. It is not touching the send buffers at all. Okay, because you are only saving incoming messages, which is your receive part of the socket. Socket buffers have outgoing and incoming. So you are only saving the incoming. You are not doing anything about the outgoing. You could have saved both, in which case you will have a different variant of this. Okay, but that's not what this algorithm does. But you could modify it. So long as you do the right thing, you could still get a good consistent snapshot. Okay? Yes.
How does this relate to exact ones message delivery and like at least ones and at most ones?
Okay, question is how does this relate to at least ones, exact ones, and at most ones? So what you should assume here is this is going to be essentially the same as exactly one's message delivery, because if we are assuming the network is reliable, okay, any message that is in transit hasn't yet been delivered will still be delivered. Okay, you're also not going to be losing messages. Okay, so messages that if you didn't have failure, they would have been delivered exactly once. Even if you had a failure, you're still going to deliver them exactly once. Okay, so this is not going to give you any different properties than each message that is sent is actually delivered eventually and delivered once eventually. Okay, it's just using TCP properties. Okay, yes. Why would you use this algorithm instead of what? Okay, why could you use this as opposed to vector clock? I suppose you could use vector clocks to also take snapshots, but you have to come up with an algorithm to do that. Vector clock is not a snapshot algorithm, right? But you got to use.
Send your vector clock to store everybody else's message that you've already seen.
Yes.
Vector clock is older.
Yes. So you could use vector clocks to reason about which messages are in transit and save them, and you will still get a consistent. This doesn't need any clocks at all. This is simply using a simple message saying time to take a snapshot. That's what we call a marker message. So it's even simpler than that. But of course, you could use a vector clock and do the same thing if you wanted to.
Well, here you have to store the TCP buffers. The vector clock does not have to store the TCP buffers.
With the vector clock, you will not have to save. You would still have to store all the messages in transit. You cannot actually ignore messages that have been sent but not received.
You only have to store the send buffers.
Yes, those are still messages in transit. If you send buffer is still a message that's been sent but not received. Yes, I mean you have to say network state and memory state. That has to be clear. Right? We have to store the state of the network and state of the memory. Okay, messages in transit is state of the network. Messages or the state of memory is the state of that process. So in either case, you still have to save some buffers. You can't, because there will always be some message that is in transit somewhere. So you got to save that somewhere. But yeah, you could modify it. I think that's true. Yes.
So I wanted to ask about the diagram you have there. Yeah, so you said if P1 starts and it says, I want to take a snapshot.
Yes.
It sends out, does it send out the markers first or does it start saving?
Yeah. So you first save and then send a marker.
Would there be a scenario where P1 sends a marker to P2 and receives the marker back before P3 ever gets a marker? Does that mess up the
Yeah.
snapshots?
Okay, that's a good question. The question is, can you send a marker to P2, get a marker back before P3 has gotten anything? That you could have any arbitrary scenario of that sort. It's not going to mess anything up because each socket buffer has an incoming and outgoing. So this is only going to do something for this connection. Okay? You might send a separate message to P3 in this case, okay? And then that might reach P3 first, or the message from this marker might get to P2, P2's marker might get to P3 first. It doesn't matter. When P3 has two markers here, whichever one comes first, it will tell it to start recording and save its snapshot, and then the other marker will tell it to stop recording.
So this ties into the question I had before, right? Because what if Q3 fails before it gets any of the markers?
Yes.
And then
So,
if you jump back to a previous snapshot, P1's going to have the new snapshot.
so if P3 has failed, okay, So this is still an partial execution of this distributed snapshot algorithm. So this snapshot is not complete. What you would have to do is maybe go back the previous hour and take a fully completed snapshot and use that.
But at that point, P1 is going to have completed this current one. So when it jumps back to the previous snapshots, you're going to have a new one in P1 and an old one in P2.
Okay, so you are asking a different question, which is how do you know whether a snapshot has been completed? Right? So to understand that, you have to make sure that all that you might have, let's say, snapshot ID. Every time the algorithm runs, you increment, saying this is snapshot 1. Next hour you do snapshot 2. So you go to the snapshot where you have all n processes that have saved their snapshot and said everything is completed. So you only load that snapshot.
So you don't just look at the most recent.
Yes. Yes. By most recent, it doesn't mean the most recent thing you return to disk while something is in progress and it failed. Most recent, fully completed snapshot. Let's put it that way. Okay. Some question here, yes.
So TCP will guarantee receiving the message, but not in order, right? So
No,
is it
TCP does
possible-
guarantee in order delivery.
Well, so it would guarantee packets in the order, right? Is it possible that the marker would come before the packet is retransmitted, and
Yeah.
that would cause some message to be lost?
No. So I think that you will see, first of all, that we are going to assume FIFO delivery. Okay, so that's a requirement. The algorithm doesn't require TCP, it just requires that the whatever protocol is being used is FIFO between any two pairs. So you can't have marker jumping over a message. If you do that, then you will lose messages. That's a given. But we are going to assume that TCP gives us that FIFO property and TCP is okay. But any technique that gives FIFO delivery, any protocol is good enough. UDP in particular is not good enough because it does not guarantee FIFO. Okay. Any other questions here? Yes, last question. Yeah.
P1 and P2 start to snapshot at the same time, and they send the marker to each other.
Yes, good question. Question is, what if P1 and P2 decide at the same time to start a snapshot and they send markers? That's okay because each is actually a distinct snapshot. Okay, what we assume is whenever you start a snapshot, just pick a unique ID for that snapshot. So P1 might say this is snapshot number 1, 2, 3, 4. The other one might say something else. And those markers have to have the snapshot ID so you know which marker is for what snapshot. Okay? So you can have multiple snapshots in progress. So long as you distinguish marker messages of two different snapshots, it's still going to give you the right property. Okay? So you will have, in that case, you're just taking concurrent snapshots initiated by two different processes. So long as you attach a unique snapshot ID to every snapshot that's in progress and tag the marker messages with that ID, you are good. Okay? Otherwise not. Yes, please.
Will the new snapshots override the old ones?
Will the new snapshot override the old one? Once a new snapshot is completed, fully completed by all processes, that becomes the latest snapshot. So you can actually start from that point on, you can override the old ones. Okay? But you have to have it completed, not partially completed. Okay? So we are over time. So we will stop here. I do have office hours. If you have any questions about exams or anything else, just stop by. Okay? Yes.